a clicker? Thank you. Hello, everyone. It's a pleasure to be here. Thank you for the very kind introduction. Let's get started. So my name is Yulia, and I work for Mozilla. The work I do at Mozilla is I work on the JavaScript compiler, and I also act as one of the delegates to TC39, the Language Design Committee for JavaScript. But I'm not going to talk to you about this, or really maybe anything visibly technical. Instead, I want to dig into the subject of this conference, this idea of joy, and take you on a walk. It's going to be a walk through a garden of branching paths. And if you find yourself dozing off a little bit, the talk is working as intended. Hopefully this will be a nice break before our final talk and before we go to dinner. Now, the idea for this talk came from a workshop at Socrates. It's a unconference for software craftspeople. And it was about 6 years ago that I attended my first Socrates, and I decided to do a session about drawing. I wanted to teach people how to draw. I love seeing the eyes light up when people realize that, oh, I can actually draw. Often people don't believe this about themselves. Now, I have a history as an artist. Before I became a programmer, I was working as an illustrator. And I wanted to bring these two worlds together. The workshop went off great. People had a great time. The eyes lit up. It was beautiful. But I got this question. Why teach programmers how to draw? What's the benefit of a programmer drawing? And I didn't have an answer for this, and I thought about it, and I carried this question for a little while. Of course, there are some clear parallels between programming and drawing. Both deal quite heavily with the concept of representation. And in the case of programming, you are representing business domains. In the case of drawing, you may also be representing business domains or something else. And both have an incredible flexibility and creativity associated to them. But something about drawing is a little different. Drawing is a physical thinking process, in particular observational drawing. There are many different kinds of drawing, many different kinds of creative processes that can be used for creating visual artifacts. And what draws me to drawing is that it is the relationship between the hand and the eye. Now, this reminded me of something, which is the game of tennis. And in particular, a certain technique for teaching tennis by Timothy Galway from his book, The Inner Game of Tennis. Why is tennis interesting? Well, the way that he teaches tennis is quite fascinating. He can teach someone to play the game of tennis within 20 minutes. But he doesn't teach the rules of the game or how to do it. Instead, he begins like this. He instructs his students to watch the curve of the ball flying through the air. And when the ball hits the ground, to say, bounce. And then when the racket hits the ball, to say, hit. And when they serve the ball up, they are to hum. Hit. Bounce, hit. Bounce, hit. Interesting that that can teach someone how to play tennis, isn't it? No rules. Alan Kay is, of course, familiar with this book. And when he came across this method for teaching the game of tennis, he said, direct quote, "Holy cow." And then he followed that up with an excellent observation, which was that the part of your brain that can play tennis doesn't speak English. And this was something that clicked for me. Yes, that is what I want to get to. There is a part of the brain that doesn't speak. It's non-linguistic. Let's get back to drawing. Is drawing linguistic? In a sense, it is, because when people approach the page, even very young people, children, when they start drawing, they begin drawing by drawing through symbols. A child will always draw a hand with 5 fingers, for example. If they're aware and can count already, they will draw with 5 fingers. There will always be 2 eyes. There will always be a nose and a mouth. But this isn't necessarily what you see in the human figure when you're encountering it. Sometimes the eye will be obscured, sometimes the hand will be in a different position where not all fingers are visible. But this is, in a sense, language. This is language on a page, not the kind of language you can speak, but it's still language because we have symbols. Myself, I began drawing quite young, and I didn't begin learning how to draw from a method. I learned to draw by tracing, and I believe that this is an undervalued way of learning. In fact, I would argue that much programming learning, especially from tutorials, is a form of tracing. For me, my moment of discovery while I was learning how to draw was I was drawing an eye, very popular subject among people to draw, and I realized as I was tracing that the eyelid had thickness. And that was my holy cow moment. I realized, wow, there is three-dimensionality to this two-dimensional thing that I'm doing. This representation I'm trying to make has a different manifestation when I observe it, when I really look at it. And tracing was doing that for me. Of course, there is theory around drawing and how to do it and how to teach it. And one particularly famous book is by Betty Edwards, Drawing on the Right Side of the Brain, where she outlines a number of different techniques, and my workshop was based on the techniques in her book. One that I like quite a bit is where you observe the palm of your hand, and the goal of the exercise is to look at every single crevice very carefully and draw it on the page as you're observing the hand. Don't look at the page. You're not allowed to look at the page, only the hand. And then after you're done and every crevice is drawn from your palm, can you look at the page? Oh, but it doesn't look like anything. That's the point, actually. It's not the goal of the end product that you have. It's the process of observation that is the goal of the exercise. Another exercise, which often lands quite well because people see something, and the process of seeing that is quite exciting, is the process of drawing negative space. You draw the air around the object. And why is this effective? What's going on when we do things this way? Well, one is you can see that it's a chair, but you are not drawing the chair. You're drawing everything around the chair that you can't name, that you cannot pin down. There are some triangles there, some rectangles, and you can't really name them, but you can understand the relationship between them. This is observation, really careful looking. Now, not to say that this kind of drawing is worse. In fact, we'll get into why this kind of drawing, symbolic-based drawing, is very beneficial. But this is certainly a kind of observational drawing. And it has an interesting impact, which is one of deferred recognition, where if you don't name what you see, if you block your mind from naming, if you allow your mind to enter other types of thinking than linguistic thinking, you might end up in a really interesting space. And then only later say, oh, that's actually an orange. Holy cow. Let's talk a little bit more about naming things. Because a rose by any other name would smell as sweet, or would it? It's not entirely clear. They've done some studies on this. So we can call this a rose, but there's other ways that we can do naming. Let's think about that a bit. One is you can break down the rose and say that talk about the constituent parts of the rose. The flower, the thorn, a leaf, a stem. Observation and naming, analysis, something that we do quite a bit in our industry. And there's an interesting way of categorizing thinkers and people who name things in this way. You might call them splitters, people who break up a whole into smaller parts, focusing on the differences between things. But there's another way to do naming, which is lumpers, broadly defined, as people who focus on similarities. So let's for a moment walk in the shoes of someone who's a lumper and think in their mode, where everything is a flower. It doesn't really matter what kind of flower. If it's a flower, it's a flower. And then you get interesting interactions between things, such as, what's the interaction here? Well, we have a metaphor. It's very spiky. What about here? Well, convergent evolution. But that's very interesting because if we take an analytic approach and we look at the bones that are involved in the mechanism of flight between these two animals, we would say, well, one's got arm bones, the other one is using hand bones. But in fact, there's something that's the same about them. How do we talk about the thing that's the same about them? And yet, this is all very useful, but we're not here to actually be useful. we can, in fact, get a little silly and realize that one is a flying rat and the other is a flying fox. Holy cow. And this brings us to another work of Borges, who will be quoted quite heavily here. And the text, I forget now I'm blanking on the name of the actual short story where this quote comes from. But the quote goes, celestial emporium of benevolent knowledge. It is a categorization. And what does this category contain? Things which belong to the emperor, things which are embalmed, things that are tame, sucking pigs, sirens, fabulous things, stray dogs, included in the present classification. Oh, geez, got recursive now. Frenzied, innumerable, drawn with a fine camel brush, etc., having just broken a water pitcher and from a distance looks like flies. How many of you have worked in such code bases? Yeah, that's what I thought. Naming things. There are problems that arise from representations. And I think they're very interesting problems. Representations give us incredible capabilities, but they also introduce interesting limitations. Here are two images of a cat. These are both representations. One is highly detailed and one is very simplified. There is a text that you may be very familiar with, or a quote that you may be very familiar with. The map is not the territory. This comes from Albert Kozybski, and he's a geologist. His argument within this text was that a representation of something is always having a reason. It always has a goal. And Borges took this in a very interesting direction in his short story. It's only one paragraph long, on the exactitude of science, where he describes a map that was so detailed it spanned the entire country, to the point that the map actually became part of the landscape. So the level of detail in a representation and the way that we work with that representation matters. How we choose to represent things matters. Let's take a look at a concrete example from our field. And this one involves genome assembly. It's one I quite like. Because, so just to describe the problem to you, a genome reassembly is when you break up a genome, you break it up into groups of 3. Each one has 3 letters from the genome. And then you need to reassemble it. So these bits of the genome are sitting on the cutting room floor, and somehow you need to reconnect them. So if you're familiar with the Königsberg Bridge problem, then you may know where I'm going with this. Now, if we consider how to solve this problem, how we do the actual reassembly, we might take each one of those pieces of the genome and represent it as a single node and try to draw lines between it. For example, TCA, let's say that's our start node, will have 2 potential paths it can take, CAT or CAG. And then from there, we can continue on and see if we can complete the path. Now, this is not something you can do deterministically. This is something that you'll need to guess and check, because there is no way to do this that is established. We can eventually find a path from this graph, but it has certain limitations. What if we could think about this differently? What if we represented it differently? Namely, instead of representing each snippet that we have as 3 letters of the genome, what if we broke it apart? And why would that be beneficial? So here, the genome's been broken up, cat, into C-A-A-T, the overlapping letter A, and we have an edge. Now, this doesn't solve the problem of we need to find the next 2 overlapping letters of AT, right? Well, in fact, it does in a really interesting way. Here's the graph that represents the same problem we saw before. But this representation fundamentally shifts how we use the algorithm. Instead of needing to visit every node once, as in the Königsberg Bridge problem, visiting every island once, we need to visit every edge once. We need to visit every bridge once. And this happens to be deterministic, and we go from an NP problem to a P problem. I like that. That's really interesting. Rephrasing and re-representing. That's a great way to work with problems you don't understand. Maybe break them up into problems you do understand, or into a shape that you understand them in. There's 2 basic types of problems, right? Problems you understand, problems you don't understand. No problem. Just transform the ones that you don't understand into problems you do understand. Except that's not quite right. There's one kind of problem. And generally, the problems you don't understand, you'll think you understand, and the problems you understand, you'll also think you understand, but chances are there's a little bit of room there for something to go horribly wrong. At Mozilla, we have something called chem-spill releases. Chem-spill releases are when we have something really bad happen, like someone found the exhaust port, and then we really need to fix something. It's a 0-day situation, and we need to make sure it works. My colleague, David Barron, my former colleague, David Barron at Mozilla, had an excellent and very interesting process for dealing with chem-spill releases. Namely, he would read the code, do the review, understand it fully and completely, and then he wouldn't approve it. He would go and from memory re-implement what he had understood the patch to be doing. And through this method, he actually discovered security issues in the thing that was supposed to solve the security issue. Well, that's interesting, isn't it? Now, I want to switch gears a little bit, maybe backtrack recursively through this maze that we're in, and think a little bit about understanding the mental modes that we can potentially be in when we're solving such problems. There's a really interesting thinker, Barbara Oakley. She's a professor of, I think, education. I can't quite remember. She has a book, Learning to Learn, and she covers these mental models, focused and unfocused. They are also known as System 1 and System 2. And for now, we're just going to focus on the focused mind. She describes the focused mind as a pinball machine, where you can imagine that like a ball gets released and it's bouncing around very tightly in this one corner of your brain. The other parts of your brain are not activated. It's just, you're focusing on this one part. That's the focused mind. And then she goes on to elaborate and says, the human brain has been studied, and we found that probably you have 4 memory slots in your brain to store stuff. You can think about this as variables or as registers, but you've got 4 of them. And from these 4, you can rearrange information, like directly access pieces of your memory to try and understand a problem, to try and learn something. I've been having a great time watching my child learn things, because I have this incredible experience of seeing her try to understand why something doesn't work. And you can see that the gears are really turning. She'll even make this little sound like, it's incredibly cute. And from my perspective, I think, well, I can totally see the problem. You're trying to put a circle into a square, and they don't fit. And you could also reach back to what we were talking about earlier with representation, and that you need to observe what you're looking at. And she's definitely not observing the fact that one's a circle and one's a square. But eventually, she'll have that holy cow moment. And what is that holy cow moment? Well, it's that moment from Barbara Oakley. She says, you're trying to fit these pieces together of this problem that you're trying to understand, and then once you understand it, it gets chunked. It gets put together. It's also sort of like, how do we understand jokes? Holy cow, it's chunked. Representation and abstraction. Abstraction is the source of a representation. A representation is sort of a reified form of abstraction. So in some ways, our representations, which we reflect on, it's like the page when you're drawing that you are getting a feedback from. It's like that exercise, look only at your palm, don't look at your page, so you don't get that feedback. So what happens when we instead focus on abstraction? What problems do we have in the space of abstraction? Well, one certainly is when abstraction does not align with evidence, and yet we have an abstraction in our head. Once we've developed an idea, once we've learned something, it's very difficult to unlearn it. We have an emotional relationship with our ideas. Why teach programmers how to draw? Well, I can't draw. I can't do math. Chunked. Let's talk about Lego. Why would we talk about Lego? So there was a really nice podcast on the Hidden Brain with Daniel Machen. It was a story about Lego, and he's a psychologist, and he's studying various aspects of the mind, and he was looking at IKEA. And IKEA's pitch is that the reason their furniture is so cheap is because you have to build it yourself. Well, he said, I don't think that's exactly what's going on. I think they're doing a psychological trick. So he brought in people, and there were two groups. One group had to build a toy car out of IKEA, out of Lego. Or it could have been IKEA. Same concept applies. So one group has to build their toy car, and the other one gets one just like that. Then, after each group had either received their toy car or had built their toy car, they were asked, how much would you pay to keep your car? Well, the group that built their own car said €1. And the group that got it just given to them pre-assembled, they said 50 cents. And the researcher had the question, Daniel had the question of, well, okay, what happens if we try to modify a couple of variables around this? What happens? Can we get those two prices to be the same? So one thing they tried was give them a really hard math problem before they build the car, and then see what happens. Well, then the price of the car goes up. Okay. Well, what if you ask them a certain question? What if you ask them, what do you value other than being competent? And get them to list that. Things that they value about themselves, other than being competent or being right. Then the car prices become the same. That's interesting. Why are we so hung up on the idea of being competent? What is so scary about being wrong? How do we solve emotional hang-ups? Well, you know what's funny about emotions is many of us have a relationship with our emotions that's very similar to that process of drawing I described where you can't name them. And here naming becomes incredibly useful, because if you can name the emotions that you're experiencing, suddenly you can reason about them. That's incredibly powerful. So what happens when we do that? What happens when we can actually call what we're experiencing an orange? But then what happens if we're wrong? Let's talk about another problem of abstraction, contradictions. How can we allow false things to be true? Because, for example, if you believe you can't draw, if you believe you can't do math, then how do you get past that unless a false thing can be true? And just to give it a sort of grounding in something, you know, there's a difference between knowing something and understanding something. There's a really interesting example in this area which comes from, again, psychology. This is the work of Dr. Vilyanur Ramachandran, and he created a therapy for amputees which involves a mirror. It's called mirror therapy. So one of the issues that happens when someone loses a limb is that that limb may continue to have a presence in the mind. And for some people, it's incredibly painful, or it's itchy. The first patient he had, the reason why it was bothering him was because he had a persistent itch in a hand that wasn't there. He knows the hand isn't there, like, you know it rationally, and yet somehow the hand is itchy. The way that he made it possible to get past this was through using a mirror so that the person could see the hand back in place. And through bringing the hand back, it allowed the itch to go away, the painful clench of the arm released, and eventually the arm disappeared. In Kurt Vonnegut's Sirens of Titan, there's an interesting chapter, Chronosynclastic Infundibula. What a word. It's just a short heading to the chapter, and what he describes, it's written in terms of a children's storybook. He describes, imagine that your daddy is the smartest daddy on the planet, and he says X is true. And then there is another child on another planet, and their parent is the smartest person on their planet, and they say X is false. There is a third planet on which, if you bring both of these parents together onto that planet, then they will both be correct. But they are saying contradictory things. How is this possible? Let's consider this in one area which all of us are likely quite familiar with, which is mathematics, in the case when 1 + 1 does not equal 2. How can this be false? Well, it can be false if it equals 10. And in this case, we're talking about number bases. So we have decimal, binary. And what happens here when we create a situation where the thesis and the antithesis are both true, we have something called synthesis. Now, you can have synthesis without having a direct contradiction between these two, but when you do have a direct contradiction, then it's a very powerful moment when you can describe two things in opposition to one another in a single system. Synthesis is very hard. It's one of the reasons why we are more likely to be taught analysis, because to teach people how to bring disparate ideas together is not something that is trivial. It's something you have to do in art school, but it's not something that's generally taught as a skill to most people. Let's get back to this mental modes that came from Barbara Oakley. And this time, let's talk about the unfocused system, system 2. So just a reminder, the focused mind is very dense. It's a very powerful way of thinking. But there's also the unfocused mind, which is not dense. And instead, you have a broad field, like spread out set of nodes that exist. So if you throw a pinball in there, it's going to bounce and then it's going to fall. Like, you're not going to have the same interaction with the ideas that are in the unfocused mind. Trying to approach it as a focused mind will not be successful. Now, the focused mind, as a reminder, is having these 4 memory slots, which then goes and acts on your memories. The unfocused mind works differently. And instead of having memory slots interacting with one another, you have the nodes interacting with one another on their own, creating connections. Now, we can link this back to the celestial emporium of benevolent knowledge, which looks like nonsense, but maybe there's actually something really interesting there. Maybe that's an unfocused mind. Maybe that's an unfocused mind of history. Using that unfocused mind, you might think, oh, can I be productive with the unfocused mind? I would say probably you shouldn't try to be productive with the unfocused mind. Although people have tried. Salvador Dali, his approach to the unfocused mind was to, when he was stuck on a painting, he would take his keys and then he'd go and relax in his chair. And he would relax as much as possible to the point that he was just about to fall asleep. But he had his keys in his hand, and they would fall at the moment he was about to fall asleep. And then he would wake up, go back to his painting, and continue. Oddly enough, Thomas Edison did the exact same thing. Well, the unfocused mind, maybe it isn't quite what's at play in the tennis case, because there are many minds, there are many subsystems to these systems of thinking. But when we don't overemphasize the goal, the point of success of playing tennis, then we learn the game more easily. Something happens when we don't approach with a goal. Why teach programmers how to draw? It's the same thing. Allow the mind to relax. Allow the mind to see things in a different way. So getting into the realm of child psychology, there's 2 interesting ways of thinking about how to raise children. And this comes from an interview in The Hidden Brain with Alison Gopnik. She describes it as carpenter and gardener. So the carpenter approach to raising kids is you have a plan, and you cut here, you nail things like this, you build a house. You have a goal. You're going to build a house. This is useful. I'm not any comments on raising children, but rather like for ourselves, for how we treat ourselves. Having a plan is great. We can build things. We can be analytical. We can solve problems. The other is the gardener. And the gardener might plant a rose one year, might plant strawberries the next. And the strawberries don't come up, only weeds come up. But that's all right, because the next year maybe we'll have strawberries again. And all of these things together give us a very interesting capability in the world. Not to do our jobs, but to enjoy the world and to allow ideas to arise. Thank you very much.